Okay, can you hear me? Let's keep going on. So this is the periodical of the abundance of the elements. So I just tell you something in the last class. So I just want you to remember that there's a very really important element in the rare earth is the deuterium Nd. Okay, this is a very important element that we use in the hard magnet. So you will see this element again and again in the following slides. Oops. So there are some features that I want to tell you is there are two kinds. There are two often seen hard magnets. One is one is look like have a black color, and the other is the silver white color. And there are very difference between these two hard magnets. And in this case, this kind of hard magnet is typically made by ferrite. The ferrite is Fe3O4, and for this silver white hard magnet, they are typically called neodymium ion boron, neodymium ion boron magnets. Okay, or you would call it a neodymium magnet. So we can compare the performance here. So for the neodymium magnet, neodymium ion boron magnet, they will contain the resonance about 1 to 1.4 Tesla, or 10 to the 4 Gauss. That would be a huge number, and its coercivity is about the 750 to 2000. In the unit would be called the Gauss, okay, and its magnetic product is about 200 to 440. But for this strong magnet, unfortunately, its Curie temperature is really low, which is about the 310 to 400 degrees Celsius. So what does that mean? If the temperature a little bit higher than the perhaps it would be 37 degrees Celsius, then it will lose its all kinds of magnetic performance. But that would be the worst case. And so the neodymium ion boron is very good, contains very good performance in those parameters, but bad in the its Curie temperature. So it is not suitable for making some kind used to the high temperature environment. So the scientists is starting to looking for different kind of hard magnet. Actually, the summation cobalt would be earlier than the neodymium ion boron, but the summation cobalt is relatively expensive than the neodymium one, because the cobalt is very expensive element. And it also have some competition between the making hard magnet and the ion battery, because some ion battery also use the cobalt as a cathode or anode material. So the cobalt is really expensive to making any kind of compound that you can have multiple application. But practically, summation cobalt have also good resonance, also good coercivity and magnetic products. The best thing is it have a very high Curie temperature, so we can apply that to the high temperature environment. For example, the vehicle motor would be always operated in a very high temperature. So if we use the neodymium ion boron then it would be lose its function at the very beginning of when you just start the vehicle. And there's another different type of hard magnet. So this is the anickel. Anickel, actually you can divide this word into three elements. Anickel means aluminum, nickel, and cobalt. So Al, Ni, and Co. So it's a kind of the alloy that contains a little bit also very good remnants, a little bit less than the neodymium magnet, and a little bit less performance of the coercivity than the neodymium iron boron, and actually it's not so good magnetic energy product. Only 110 to the 110 or 210 to neodymium iron boron magnet, but its working temperature is also high, so it will be reached to 700 to 860 degrees Celsius. So that will be also good. Okay, so shown here is another plot here, that, and here is the this is the magnetic energy product in the y-axis, and this is the year. So in the beginning, our human being developed the magnet since the actually we can go to very early years, but I think for systematically to discover the magnet will be started at 1920. So we just start from the pure element cobalt and the alloy at the 1940s. Then we find the anickel have contains very good magnetic energy product. Then we also find the other alloy is called platinum cobalt, which is also very good hard magnet, but that would be very expensive because the platinum is expensive element. And then we found the Samaritan cobalt with different mixing ratio, which is 1:5 and 2:17. Then at the end, almost the end of 1980s, we found the neodymium iron boron, and then we found a way to increase its performance like sintered neodymium iron boron. And nowadays we still have the most used hard magnet is neodymium iron boron. Scientists already improved its Curie temperature a little bit about. So for the most applications that we can use the neodymium iron boron for the source of the DC magnetic field. Okay, just lose my control a little bit, okay, for a while. Okay, so let's introduce the whole history of this hard magnet. So before the 1930s, we used the magnetic steels. That is the steels with 3.5 chromium and 6% tungsten, and the cobalt with 17 or 36% in the steel. So we can make a magnet steel. its coercivity is about the 250 Oster. And then we discover the alloy magnet. So the first one we call the Remery. So it's the alloy that mix with the molybdenum, cobalt, and the iron with the ratio 17 to 12 to 71, or in different ratio is 20 to 12 to 68. Its coercivity is very close to the magnetic steel, and it's probably to 250 Oster. And at that time, we developed a lot of the alloys. So there's another alloy called conifer. Conifer is also something like nickel. The conifer is composed with cobalt, nickel, and iron. So that would be the mix with the ratio between iron, nickel, copper is 20 to 20 to 60. Here also the same. I do not want to repeat that again. So there's the conical and the vicoli. So they have different 3D element and its different composition ratio. Those series of material have a coercivity is about 250 to 680 Oster. And then the nickel appears. So the nickel alloy was developed after the 1950. Okay, its ratio it was composed with the iron, aluminum, nickel, cobalt, and copper. So the ratio is very complicated. You can just check here, but for the nickel here we can find it. This is the first one hard magnet that we will have the magnetic energy product reach to the 100. Of course, its Curie temperature is also high, so we can use that in many practical usage. And its coercivity is about 440 to the 1600. And then there is the iron, chromium, cobalt. This is a different kind of hard magnet. It's discovered after the 1971. So it contains iron, chromium, and cobalt. And its coercivity is roughly about 600 to 800. And then there's a new hard magnet we call Lodex. And the Lodex is a very important hard magnet because it contains a very important feature, which is they have a very very good magnetic field that we can use to some accurate devices such as a microphone relay, or use that to make magnetometers. And this Lodex is composed with the iron and the cobalt with a different ratio, and its coercivity is about approximate to 1000 Oster. And then we also found platinum cobalt alloy, and platinum cobalt alloy have a very high coercivity, which is reached to 4400 Oster. But in this alloy, it is very worse that we use the platinum, because the platinum is very, very expensive. And then people realize that all of above elements is made by the elements that only contains 3D electrons. So if you want to improve the performance of magnets, they need to looking for new kind alloys that contains F electron. So at that time, people know how to extract the rare earth from the minerals. So that would be the first time we can use the 4F element to make hard magnet. So after the 1980s, people knows we can make a rare earth. Okay, that would be maybe I missed the rare earth alloy. Okay, it's not rare alloy, it's rare earth alloy. Okay, we can make a hard magnet with a rare earth element. So the first rare earth magnet, it appears with cesium mixed with cobalt. So the best idea is that the cobalt is a kind of, we already know the cobalt is a very good magnet. If we mix some cesium, maybe we can induce the magnetic order of the cesium, and the cesium contains the 4F electron. So we may create a very huge internal magnetic field, and that would become a very good hard magnet. So from the 1968, they make the first cesium cobalt, and it did have a very large cohesivity, which is about 7,000 to 9,500 Ørsted. So at that time, that would be a world record of hard magnet. But it is still they still have a problem because the cobalt is very expensive. Although and at that time, rare earth is also expensive too. So although they can make a very strong hard magnet, that would be not so popular, and people are still looking for some substitution to cesium. And then the neodymium ion boron appears, and neodymium is also expensive at that time, but it's not so expensive. And the ion and the boron is a rich element inside the in the earth. So we can mix these three elements and build a new rare earth alloy hard magnet. So that was first discovered at the 1983, and its cohesivity is stronger than the cesium cobalt, which is about the almost 1 Tesla. 1 Tesla is 10,000. Okay, so its cohesivity is about 1 Tesla, which is also the world record at that time. But you know the disadvantage of the neodymium ion boron magnet is its Curie temperature is really low at that time. So you can just use your hand to make this magnet lose its magnetic property, because the Curie temperature is 310 degrees Celsius. So your body temperature is about 36 degrees Celsius. So use your hand, you can make the neodymium ion boron magnet lose its magnetic property. So people try to increase its performance. So you can find the neodymium ion boron have 2 points in this figure. And this one is disintegrated the neodymium ion boron, and it contains large cohesivity and higher Curie temperature. So typically you can buy the neodymium ion boron is this type in the bookstore. And at that time, there are still other scientist group. They are still developing different kind of alloy. For example, the iron platinum. The ion platinum is also very expensive in the platinum, but you may curious why people still want to use the platinum, because the platinum have a very good chemical property that can resist the different kind of environment, such as if the environment contains some oxide, right? So the people still want to looking for hard magnet contains the platinum, and so this kind of the hard magnet developed after the 1984, and its coercivity is property 4000 Ørsted. It is relative. It is only a half value to the Newtonian ion boron, but it have its importance that we cannot substitute this kind of hard magnet to Newtonian ion boron. And there is another different series that is made by the cobalt-zirconium or cobalt-hafnium. And in this case, because they have very high permeability that they can use to making in the electron devices that can isolate the electric field. So this kind of hard magnet is discovered after 1971, and its coercivity is probably about the 4400. Okay, so these are the families of hard magnet. So we can make a very short conclude is the hard magnet, most hard magnet families contains coercivity is about or it will be less than the 4000 Ørsted, and its Curie temperature is from 400 K to 800 K, and the most thin strong hard magnet is the Newtonian ion boron. Okay, that's the brief introduction of the hard magnet. Any questions? No? Okay. So let's go to the next section, which is the soft magnet. So what is the soft magnet? That based on the definition, the soft magnet contains the coercivity less than the 20 Ørsted. So the soft magnet materials are those materials that are easy magnetized and demagnetized. Okay, so magnetized means that they can become magnet, and demagnetized means that they can be lose its magnetic field instantly. So the soft magnet material is very important thing that can make inductance that I will show you later. So there are two types of soft magnet. One is the metal, so iron, cobalt, and nickel plus silicon or aluminum is a soft magnet. And the other is a ferrite. Ferrite contains the spinel structure, which is the iron 304 plus nickel oxide, zinc oxide, and manganese oxide. Okay, so those material you can use it in the transformer or inductor core or recording head, even in the microwave device. So that would be very important nowadays, because you know your cell phone is communicated with the electromagnetic wave in the range of the microwave. So its wavelength is probably about 2.1 or 2 to 5 centimeter. So in this range is the microwave range. So that would be very important to use the microwave device, not only in your microwave oven, but also in the telecommunication. Okay, and the soft magnet also can make some magnetic shieldings. And this type of applications for the soft magnet, we can fall into the two main categories for the AC usage and the DC usage. So in the DC applications, we can say this material can magnetize in order to perform we can operation and then demagnetize then at the conclusion of the operations. For example, this is a very large clamp that can scrape some metal with ions. So you can switch to attract scrap steel and then switch off to drop the steel. So that's for the soft magnet for the DC usage. So typically that we want to it become magnet at a moment and lose its magnet properties at another moment. So we can use the soft magnet in the AC applications. That is, this material will continue cycling from being magnetized in one direction to the other, and throughout a period of operation. So we can use the AC power here, and then there will be magnetized with the different directions from. Maybe the direction would be at this direction from the bottom to top, and then at another moment that would be magnetized from the top to bottom. Actually, we can say this function is work with the high permeability, which is desirable for each type of application, but the significance of another property varies. So for making this kind of the transformer, we need a very good soft magnet that contains high permeability, and then we will not lose the magnetic flux outside these devices, because if there is some magnetic flux outside this transformer, that means you will lose the energy. So high permeability is very important, and the scientists still discover some very important soft magnet to increase its high permeability. That's the basic idea how to make the transformer. Okay, any questions? No? Okay. So in the above section, that would be very traditional usage of the magnetic materials, and I will give you a short review for those classical or traditional traditional property of the magnetism, and then the following section would be go to some novel materials. And this material may not used to create a very large magnetic force or used to transmit energy, but that novel magnetic material will be very important in nowadays, because they can store the information, or they can use to some medical usage. So that would be also very important in this material catalog. But before that, I will give you a very short review of the previous classical magnetic material. So we know the relation between the spin and the magnetic ordering. We just start from the an electron that orbiting the nuclear. I already told you this is a very basic concept, but it is totally wrong in the real quantum mechanics description, because the electron would not really orbit the nuclear. It's spread like a probability sphere around the nuclear. Okay. So we just start from here, because we want to define the what is called the Bohr magnon. So we know the electron is orbiting the nuclear with certain angular momentum is mvr, and if we want to define the magnetic moment, mu L is the current that surrounding this area and times the area. So mu L is equal to IA, and the A is equal to pi r squared. So the current is charge per unit time with past any point on the q times the frequency of the rotation. So we know the I is qf, which is equal to the qv by 2 pi r. And then we define the Bohr magnon here, which is mu b equal to the qh bar by 2me, and the unit of Bohr magnon is 9.27 by 10 to the minus 24 joule per Tesla. And there are two kinds of Bohr magnon here. There are two kinds of the magnetic moment here. One is coming from the orbiting motion, which is the mu L, and the mu L is equal to minus GL mu BL by h bar. And the other is angular momentum, or magnetic moment, is coming from the intrinsic angular momentum, which is mu s is equal to minus gs times mu b times s by h bar, and s is the intrinsic angular momentum. And here, compared to the orbital angular momentum, this is the real electrons that surrounding the nuclear. So this is the real angular momentum, and this is the intrinsic angular momentum. And furthermore, we know that the GL is equal 1 for the orbital angular momentum, and the GS is the factor of 2 for the intrinsic angular momentum. Okay, that's a very short review for those classical magnetism and classical magnetic materials. And now we are going to next section. And this section we were talking about some devices that made by magnetic material, especially for some information storage. So the first one is called Spintronics. So what is called Spintronics? Spintronics is also known as spin electronics or fluxtronics. Okay, as its name, Spintronics means we use the electron spins, or we use some tronics means some particles that would be pass through, because this is flux, pass through certain point. So it's called fluxtronics, or spin electronics, or spin electronics. Okay. So the spintronics is the study of the intrinsic spin of the electron, and it associated with magnetic moment, in addition to its fundamental electron charge in solid state devices. So you can imagine that typically we use the so here is a conduction wire, and we use the current here to deliver energy. So you just plug your plug, and then you got the energy through this current. But do you ever think about if this current contains spins such like this, then we can not only deliver the energy through the conduction wire, maybe we can also deliver the signal here, because you can define the, for example, the spin up may be defined as 1, and spin down may be defined as 0, and maybe this is 1. So when you plug the your plug, you may get the both energy or information. So the energy would be extracted from the P equal IV, or P equal I is means the Q dt per V. And maybe you can get information from the spin magnetic moment, which is G mu B S. Okay, S means spin. So if we can do something that we can polarize the spins of the electron in the conduction wire, then we can get both the energy and the information. Okay, so that's the basic idea why we need to develop spintronics. Okay, so spintronics emerged from the discovered in the 1980s. Okay, we are concerning spin-dependent electron transport phenomena in solid-state devices. Okay, so in that case, we are not put the spintronics inside the conduction wire, but we put that in the solid-state devices. So maybe they are not very good conductors, but we can at least we can control the spin orientation. So the spintronics include the observation of spin polarized electron, injection from the ferromagnetic metal to a normal metal by Johnson and CDB. Okay, so what does that mean? Let's go back to a very early section that we already mentioned. You can imagine that what is called ferromagnetism or ferromagnetic material. So ferromagnetic means that we have atoms that carry spin parallel to each other. So if we have another electron eject to the ferromagnetic material, we can use this ferromagnetic, the spins of this ferromagnet to polarize the electron spins. For example, in the beginning, maybe the electron spin like this, but when we go to here, these spins would be affected to become a little bit parallel. Maybe like this. And when we go here, that will be more parallel here. Then finally we got the parallel spin of the electron. Okay, so we can use ferromagnetic material like a polarizer and polarize the electron spin to the wish orientation. So the principle is use the ferromagnetic metal to ferromagnetic metal. Okay, so here is an example. So this is the material that have the 100 micrometer width and the 50 micrometer thickness, and there is a window that we can inject the current here, and of course this current contains a lot of the electron which is not polarized, and then this electron will pass through this distance from x equals 0 to x equals L, and then we set up a detector here to check the polarization of the current. So we can use an equation like this. The Im means, okay, magnetization current. So it is not real dq dt. It is counting about the magnetic moment per time that pass through arrow point. Okay, then the equation is that we know the minima or the unit of magnetic moment is mu b, right? This is for the unit, and we know. Okay, we know we inject a certain current here, so we have I in the equations, and if we divided I by E, then we will get the total number of the electrons. For example, I can write here. Okay, wait a moment. Okay, we know I is equal to this. So if we know the definition of I is dq dt. So if we divided I by E, which is means I can do that dq E dt. So this is a typical number of electrons. And what does this mean? We know this is the number of electrons. So number of electrons divided by T means the unit time of electrons pass through a certain point. Or pass through a point. Okay, so this one tell you the number of electrons pass through a point, and if we times mu b, that means we have the total magnetization that pass through a certain point. And the eta is okay, we'll go back here, and the eta is a phenomenology coefficient, and this value would be less than 1 because this is the okay, I will explain that later. Okay, so this is an example. We know the speed, magnetic moment that comes from the spin is mu s. The mu s is equal to minus gs mu bs by h bar. Okay, and we know the single electron contains half h bar spin, and we know that gs is equal to. So if we insert all this value to the mu s, we will get a single electron carries minus mu b magnetic moment. So if we have 5 ferromagnetic, actually that would be not so accurate. If we have 5 electrons, then they are all parallel. So if they are all parallel, we have mu s is equal to minus 5 mu b. Okay. But if we just flip one spins to down, then the sum of this magnetic moment would becomes minus 3 mu b. So that is the reason of the equations we just write. The Im is equal to eta times those magnetizations, because eta at least that would be 1, right, for the fully parallel current. But if in the case of here, the eta value would becomes 3 by 5. So that's the meaning of the eta. Okay, any questions? No? Okay. So when we inject the current here, okay, of course this current would have a random orientation, and when it passes through a certain distance of ferromagnetic material, then we will get the polarized current, and that's the things that we want to do. Okay, this is the original paper that comes from the that would be written by the Johnson and Series B. Okay, so that paper is the first paper we just described about something called Spintronics. But Spintronics also include various types that we just want to control the electron spins in devices. For example, there is one more Spintronics phenomena called gyromagnetoresistance. And this device is independently discovered by the Aberfeld and Peter Gussberg. And we know the Aberfeld got a Nobel Prize because the discovery of the GMR effect. So in these devices, they make the thin film alternately grows by iron and cobalt. He made at least 10 layers of these thin films, and he measured the resistance between these 10 thin films. And that shows the different resistance when here is an external magnetic field or lack of the external magnetic field. So he found a very huge difference resistance or resistance change under with or without magnetic field. So this effect is called GMR. So we will talk more about the Spintronics later. Let's take a break for the 10 minutes.